Okay, in this video I want to talk about something called an isomorphism. And conveniently, this gives us an excuse to revisit our favorite linear algebra theorem. If T is the linear transformation from V to W and has standard matrix A, which is a square matrix, which actually means the dimensions of V and W are the same, then the following are equivalent. And we've already seen a million things that are equivalent to A being invertible, and we were going to tack on a couple of new ones. So we already know that if A is invertible, its determinant is not 0, which means that it's called non-singular. If it's invertible, its inverse exists. If these things all happen, then the rows or the columns should be linearly independent. Ax equals b should have a unique solution. For Ax equals 0, that unique solution is the 0 vector. It turns out if you have n linearly independent rows, your rank is going to be n. The nullity is going to end up being 0, which actually is going to tell you also the kernel. So remember, we had rank plus nullity as the dimension of the domain. And so if rank plus nullity has to add up to n, rank n means that the nullity has to be 0, which means that the kernel has to be 0 dimensional. So the kernel has to be just the 0 vector with nothing else. If this happens, we say that T is 1 to 1. And this is actually the same exact definition as a function being 1 to 1. It means that you can't have two different vectors being sent to the same place. Okay. Second definition. So definition of 1 to 1 we've seen before and everything from college algebra on up. Now we're just saying this ties into everything about invertible matrices. Okay. So a linear transformation is called onto if the range is equal to the space on the right. So everything in the output space is T of some vector from the starting space. Okay, so now we can define what's an isomorphism. An isomorphism is a linear transformation that has both of these properties. It's 1 to 1 and it's onto. Okay, so if that happens, we also say that the two vector spaces themselves are isomorphic. So they're equivalent under an isomorphism, basically. So an isomorphism, iso meaning same, morphism meaning transformation. It's a transformation between things that are the same. So we're saying that these two vector spaces are in some sense the same, or in some sense equivalent. Okay. Let's look at an example. Try and show that the vector space M22 is isomorphic to P3. So M22 is all things that look like a 2 by 2 matrix, so an A, B, C, D. And P3 is a set of all polynomials of degree 3 or lower, so ax cubed plus bx squared plus cx plus d. And in order to show that these two are isomorphic, we have to actually come up with an isomorphism. So we need a linear transformation that goes from this set into this set. Hopefully one that's both 1 to 1 and onto. So I'm just going to define the most intuitive, obvious thing I can think of. I'm going to say that T of a matrix ABCD is equal to the polynomial ax squared plus, ax cubed plus bx squared plus cx plus d. So there's a lot of things we would still have to check, and I'm not going to show every little detail, but it turns out it is true T is a linear transformation. We would have to check that T of matrix plus matrix is equal to T of the first plus T of the second. We'd have to show that T of a constant times a matrix is a constant times the answer, T of the first. Other things that we need to check that the kernel of T is the 0 vector. So let's take a look at the kernel of T and try and see if we can figure out what is the kernel of T. I really hope it's a 0 vector. So let's see, the kernel means all things that get sent to the 0 vector. So if the output is equal to the 0 vector, that means ax cubed plus bx squared plus cx plus d has to be 0. So each of these coefficients, a, b, c, and d, has to be 0, which means that our starting vector, a, b, c, d, must be 0, 0, 0, 0. So I think the answer is yes, the kernel is the 0 vector. If I write down maybe some of the steps that I was just saying out loud, if ax cubed plus bx squared plus cx plus d is equal to 0 vector, that's t of a, b, c, d, then the equation on the right tells us a and b and c and d are all zeros, which means that the vector a, b, c, d is 0, 0, 0, 0, which is the 0 vector. Okay, so if something is in the kernel, if it gets sent to 0, we show that, oh, it has to be actually the 0 vector in the first place. Okay, and last thing we need to check, that's a cat, is that the range of t is equal to the entire output space. So let's check and see what is the range of t. Let me brush some hair off of here. Okay, looks good. Okay, so the range is the output. What are all outputs going to look like? Well, t of anything is going to look like this. More hair. T of anything is going to look like this, and anything in P3 is also going to look like this. So I feel like anything in P3 is going to be some output of some starting vector in M22. So I think we can just go ahead and say that, yes, the range is equal to P3. So the kernel being the 0 vector means that t is 1 to 1. The range being the output space means that t is onto. And if t is both 1 to 1 and onto, that means that t is an isomorphism. Sorry, t also has to be a linear transformation, but we did write that down. And that means that M22 and P3 are isomorphic. And so in some sense, they're doing the same thing, or they're equivalent to each other. And you can run through this argument for pretty much any two vector spaces that have the same dimension. If V is a 7-dimensional vector space and W is a 7-dimensional vector space, you should be able to come up with a transformation that turns one into the other. I'll let you guys think about that.